Hello everyone. Welcome to today's presentation. This is the third and final presentation in this three-part coffee break series on meshing in SRAM and panels. And today we're just going to be going through some of the commonly asked questions we get in technical support. Some of you actually asked these questions in advance, so this is kind of meant to be a prearranged Q&A session, I guess you could say. Not one single topic other than, I guess, meshing and SRAM that we're covering, but hopefully it provides you some more insight into questions that other users might have had. So I tried to list the questions here in a general sense, whatever can fit on one line. And so you'll see here we've got questions related to, well, why isn't my panel meshing? Some of these are fairly general, but we've tried to boil it down to kind of the more commonly occurring situations, looking at how we can integrate panels into the mesh. Can I choose which panels are being meshed and exclude certain panels? Can I generate circular holes in my mesh? Are there ways to quickly model walls or vertical panels of other types? And how do I get results from my mesh at points of interest? So we'll answer these questions, and if there are still questions beyond this, at the end we'll have time for a Q&A as well. So let's just jump right into this, and I'm going to start with the very first example that I'm working with. And this would be a scenario that I envision happening related to model tolerance and potentially models not meshing correctly. So in this example here, I've got three different panels. It can be a little bit hard to see the third one because it's very small by design. But I'm going to turn on the display of the dimensions, and you can see here this model, or this panel on the top is 10 meters wide. We have another panel next to that that's 1 meters wide. And then next to that, we have one that is 0.1 meters wide. And you'll also notice here, if I display the mesh density, which if you attended our previous presentations, you'll know what that is. It's basically an instruction to the meshing algorithm to say that along the longest edge of each panel, we want to have X amount of elements. In this case here, 10 amounts of elements along the longest edge. And you can see each one of these has a mesh density of 10. So let me go ahead and try meshing this. I'm going to turn off the display of the meshing density. So I'm just going to click on this button right here, mesh panel elements of type membrane, plate, or shell. I'm not going to change anything else. We know the same mesh densities exist throughout. And naturally, we should expect that on the left-hand side, we have much larger panel with the same mesh density. It should have larger shell elements created than the panels next to it. So let's try and mesh this. I can press this button. And you can see we get this, this display here that says confirm the quality of the mesh. So I'm actually going to, what I'll do actually is I'll just, let me retry that again. Sorry, I'm going to remesh this with the same instructions here. And you can see here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements along the longest edge. It's a square panel. So naturally we'll have the same mesh density on each panel edge. And if I scroll down to this one, you can see here that we're also getting 10 elements. It's just those elements are smaller because the panel's smaller. But when I get to the really small one, that's where I run into an issue. It hasn't actually meshed anything in this particular panel. You might remember again the element size that we were using. This panel element size was quite small, about 10 centimeters. So naturally, it would produce about 1 centimeter size shells if it were to mesh correctly, because we have a 10 centimeter length on the longest edge and we have a mesh density of 10. So let me just get rid of these. And to get rid of these, if you may have recalled from previous presentations I've done, we'll use a quadrilateral element tool. And because I've only created quadrilateral elements, I can use this tool and hold down the control button on my keyboard and left click and drag around all of these panels. And it's going to get rid of all those quadrilateral elements, but it's left behind the joints. But most of these joints aren't attached to anything anymore. So I can get rid of those too using a similar technique. I'm just going to use the joint tool. And I'm going to left click with the joint tool selected, but holding down control on my keyboard. So hold down control, left click and drag. And it's going to get rid of all of those panels or all of those joints as well. And with that, we can say that we've got a kind of a return to our original model. Now, I want to investigate something called the model tolerance. So I'm going to go to the File menu. I'm going to go to Integrity Checks. And there's other ways to access this through the Run menu, for example, the Run dialog. But you can see here we have a model tolerance. And this model tolerance basically dictates kind of the fear of distinguishability, for lack of a better term, between different joints that might be closely spaced in your model. So in this scenario here, we've got a model tolerance of 0.05 meters, of 5 centimeters, which is greater than the distance between the shells that I would generate if I were to mesh that smallest panel, because remember we said we have 10 centimeter length of panel, or width of panel, and we have a mesh density of 10, so each shell would be approximately a centimeter. So this is too large because S-frame isn't going to be able to distinguish between those 1 centimeter differences in joint locations with a larger model tolerance. In this case here, a 5 centimeter model tolerance. So let me lower this, and I'm just going to be a little bit more conservative, and I'll say here, let's go to 1 millimeter, which I think is a good starting point for most applications. As you can see, when we get into really small elements and components, you might want to lower this model tolerance. But 1 millimeter is usually a good catch-all kind of value, and I think it works for most of our users. And I'll click OK again. And now I want to just remesh this. I'll click Mesh Panel Elements, type membrane plate or shell. And if I've done everything correctly here, I should be able to zoom in, and we can see here there's a very dense array of joints. But now I can see that it has produced that. So if you do have maybe a large panel, a large model tolerance or a small panel, you may want to consider revising your mesh density, or model tolerance rather, if your mesh density necessitates a very finely spaced joint pattern. So that's the first problem that we've come up with here. I'm going to go to the next one, and this next one looks, again, kind of like an odd arrangement of panels, and most of our users would never need to create something like this, but I do think it is a helpful way to illustrate actually two different concepts in S-frame. So the first one would be, well, how do I just mesh one of these panels? Maybe I've got a bunch of them, but I'm not quite done defining everything in some of these panels. Maybe I've got some internal nodes to add, for example. How do I just go about meshing one of them? And it's quite easy to do. You just need to unselect the panels that you don't want to mesh. So I'll just get rid of the selection of this one. So I'll unselect that, unselect this one as well. And I'm just going to leave this one here selected. And then we have this command at the bottom of the screen. And you can see here at the status bar, we can hover our mouse and we get a tooltip, and it says mesh select panels and seed nodes only. So I'm just going to toggle this guy on. And when I toggle this on, we're going to be able to mesh this panel elements and type membrane plate or shell, but it's not going to mesh the ones that are unselected because I toggled this off. So that's how you control that. Maybe just as an illustration here, if I reselect these and I turn this off. Actually, let me revise that. So I turned this mesh selected panels and seed nodes only option off. I'm going to unselect these again, just like I did before, with the only difference being that now I have this toggle turned off. And now I can go into mesh panel elements and type membrane plate or shell once again. And you can see this time it's actually generated a mesh for all of them because I didn't have that toggle on. So even if a panel is unselected and we click the mesh button, it's going to mesh all the panels in the model unless we've specifically told it to only mesh the selected panels. I can click no here again, and this actually leads into another situation that I wanted to address. And this one here is, let's just say, for example, that we're looking at these panels and we won't have kind of a consistent element size. Connect these elements together with other objects down the road, and we just want to mesh them in advance. Right now I can see with the mesh density, we have a varying mesh density. So two of them have a mesh density of 10, and this one up in the corner here has a mesh density of 30. We saw already what the mesh looks like when we mesh without any other parameters adjusted, but we already know, based on our knowledge of mesh density, that this one's going to have 30 elements along the length of its longest edge. So it's quite a dense mesh. This one's going to have 10 along its longest edge, so it's kind of in the middle. And this one has very long edges, but still a mesh density of 10. So this one's going to have the coarsest mesh like we saw. But if I wanted to average that, we actually have this command here at the bottom of the screen. It says average the mesh density for all panels. I'll toggle this on, and I'll click the mesh button again. And you can see it's now produced a much nicer looking mesh that basically takes the average of all the density, or all the elements that we have and their mesh densities, and produces a shell element size kind of consistent across all of them. One other topic I'll bring up here is kind of segueing into what we're going to discuss in just a minute, and that's how we integrate members and other objects into a mesh. So let's just use an example here where I've got this 1 meter mesh, and I want to integrate, basically force the mesh to connect to different objects. And the thing to note here is that we have different types of nodes in S-frame. We have, for panels, we have nodes on their edges of the panel, like the vertices, which are helpful to kind of lay out the dimensions and so on. But we also have internally, we have seed nodes. So if I just add a node here, and maybe I'll add another one, I'll click just a few spots. You can see here we're just kind of dotting some nodes inside the panels. And if those nodes are inside the panels, it will basically give the meshing algorithm a point that it has to grab onto and create a mesh around. So it's going to connect that to the mesh. So if I had to remesh this guy, you can see here that I didn't really highlight it very well, but we have perhaps a bit of a distortion in our mesh around those internal nodes that we've added, because S-frame is trying to accommodate those. Now, what I could also do is I could increase what we call the seed density of our panel. So right now we have this, we're familiar with the parameter mesh density, where we have a mesh density of 10. But I can go in and I can say, let's modify the mesh parameters, and I'm going to change the seed density as well. I'm going to change the seed density, which is currently set to, what is it set to? 1 for each of these panels. And I'm going to change it for this panel to equal 3. Just got to increase that here and apply it to the panel handle. So now we have a seed density of 3. And if I remesh this, we're going to see that I turned off the average mesh density, but we see that we get a higher concentration of elements around those nodes, because the seed density is basically saying, well, maybe those nodes are representing columns or load application points where I need a finer mesh to capture the behavior in that area. This allows us to accommodate that. So if you wanted to have perhaps more of a concentration of density of mesh in one area, the seed density may be a way of doing that. And there's actually a really kind of, I think, a helpful schematic to explain this. If you right-click on the panel element tool, and it brings up this dialog, and then there's this mesh density command, you can look at all the different parameters and really better understand what they might represent. So let's just say we have a mixed mesh, which is a mix of quadrilateral and shell or triangle shell elements. And here we can see for this panel what a mesh density of 10 looks like. If we increase this up to 50, we'll see what that looks like. It's much denser naturally. We also have one whole panel, and we have one internal panel that might have a different density, for example. So we can have a different density in that internal panel if we really wanted to. Let me back this down a bit and say I want internally a finer mesh around that internal panel. We can also control the seed density. So right, like we saw, we have this 3 internal nodes in this demo panel that we have in this dialog. And I might want to back this off and say, I want to use a seed density of 1. Now it's just going to create a fairly uniform mesh size around all these, just making sure that it connects those nodes to the mesh. Because where we have connection between the mesh and the shells, and the nodes is where we transfer forces between those. So with an internal seed density of 1, it's going to give us something that looks like that. If we increase that even more to, say, 10, we get a much finer mesh in those locations. And that kind of segues into my next exercise, where we might want to consider this frame structure, where we have a variety of different beam elements, column elements, and eventually I'm going to draw in a panel on top. So I'll draw in this shell mix mesh panel, give it a thickness, I'll give it a material property, and let me also define I'll say a reasonable mesh density, which is a subjective term, so don't read too much into what I'm putting here. But I'm just going to draw this in. And you'll be able to see pretty quickly here that we've got this shell elements that are produced, or sorry, panel elements that are produced. And with our knowledge of the importance of nodes along the length of our panels and internally in our panels, we should understand that the tops of our columns should get captured by the meshing algorithm. So when I go ahead and click the mesh panel elements of type membrane plate or shell, it's going to produce for me a mesh that basically ensures that all of these column joints are integrated in the mesh. However, if I'm going to zoom in a little bit more, we can actually see that we've got our beams, and some of those beams aren't nicely integrated into the mesh. So they would really only be connected to the mesh at the start and end points. And if I wanted to actually integrate those better, what I can do is basically subdivide those for the purposes of meshing. So let me just select those beams and only those beams. So I'll unselect everything else. Just select these beams here. And I'm going to go to the sub command, which is right up here, this division symbol. And I'm going to change the member subdivision size. I'm going to say, let's just have 5 links along the length of that member. So I've added a bunch of new nodes, which basically give me, I call them hooks to the mesh to grab onto. And now when I do this, I'm going to mesh. And the mesh might look a little different because we've got all these nodes that we can apply to, and we haven't adjusted our seed density and everything. But the important part here is that all of those nodes will basically act like magnets for the mesh and ensure that we have points along the length of each beam that are connected to that mesh. So we're going to have better force transfer and so on. How many nodes is ideal? It really depends on the application, and we recommend kind of playing around with these values if you're not experienced with it, because every application will be a little different. But hopefully it gives you an idea of how this looks and how it works. And obviously, coordinating with your mesh density and your seed density can give you a really nice mesh. Okay, continuing on here, there were, I think, 2 more items that I wanted to touch on. And one of them, actually 3 more. I'll go to the first one here. This one, again, looks a little odd on the surface. I've got 5 nodes, and I'm actually displaying my nodes. So I've got my display of joint numbers turned on. I have 1, 2, 3, 4, and 5 in the middle. And what I want to do in this scenario is I want to use these as kind of a guide to produce a circular cutout in a mesh. Now, there's different ways you could do this. You can generate a clone of a joint and basically rotate it about a specific axis and produce a nice circular array of geometry, which can be helpful for that as well. But if you don't want to go through that effort, we also have under the mesh command here the ability to use some of these wizards that are basically, well, you can see the names, mesh circular cutout, for example. So here I'm going to go with this option. Let me just move out this dialog. And you can see what this looks like. So there's a reason I'm displaying my joint IDs, because this gives me the ability to define an I, J, K, and L joint, and then a C joint in the middle. So as you can probably guess, I'll use joint number 1 is my I node, 2 is my J, 3 is my K, and 4 is my L. And I can specify my I to J links. I'll say here I've got 10 links, and J to K, I'll do 13. I'm just making these numbers up. I'll say 7 and 8. Then we want our C node, which is the internal node here, our column part of our whole. I want this one to be joint number 5, and the radius, well, I'll say that it is 1 meter radius. And then we have control over mesh factor and so on. You can see a little description of what that means, as well as the radial links. So I'm going to set the radial links here from the outside diameter to the corner node. So you can see from here to here. Let me just go with a value of, well, I'm going to change this to quadrilateral. I'm going to go with a value of 10. I'm not sure if this is going to produce a perfect mesh, but we can fine tune it again as we saw. I'm going to click OK. And you can see what it's generated, this kind of spider web look to the mesh layout. Now these are shell elements that were not produced with the panel, so I didn't have to click the mesh button like I normally would. But we can still subdivide these. We can tweak it to what we want and produce a finer density mesh with those parameters that we have. And as you might have seen, under the mesh command here, we have different tools for meshing curved surfaces, quadrilateral cutouts, and we have obviously seen the convert members to meshable panels command as well. So 2 more items left here. I'm actually going to create a new file now. File new, and I'll just create this one with all the default parameters. And this question that came in was related to basically quick ways to model walls. And there's a lot of different ways. And one way that I personally like is to use the multi-story builder functionality. We've got a lot of YouTube content on that. If you're curious, just search in the S-frame multi-story builder. It's more of a workflow for creating multi-level structures, but a lot of that can be kind of replicated here. So here I've got my grid, I got my structure model ready to go. And I'm going to click on this panel element tool. And you can see here with the panel element tool that we were using before, we can configure it to set up our desired thicknesses. We can specify our materials. So I'm going to go again with the concrete material. And then we have the type of panel that we want. And next to that, we have this pattern. So I can define here with this pattern the type of panel I want, a wall panel, but there's obviously other options like a wall with link beams or a wall with openings. I can specify the height that I want to use. I'm just going to say here we've got a 5-meter high panel, and all of the other parameters are related to this as well. So mesh density, seed density, this can all be configured. And then I just left click and define the location I want to apply this to. So the start point and the end point. And it's produced a panel for me, and I can do this in a couple different ways. And it's produced that panel for me as well. And if I actually shrink these elements, you might notice that we have these nodes at the top, or these members at the top and bottom, which might sound a little bit odd. But what these are, if I switch to the member type tool, is these are wall integration lines. So when we mesh a wall, we're going to have all these shell elements that will give us contour results like the distribution of forces and moments and stresses and so on across that wall. The wall integration lines will actually integrate those results at those points of interest and give us results in a format that might be more consistent with our expectations for design and so on. So let me actually just mesh this. I click the mesh button. I've got a fairly fine mesh for this wall. A lot of times you might not need this fine density depending on the application. It's up to you really. And then I'm just going to apply a fixed support at the base. And let me also apply a couple loads. So here I'll click new load case, and I'm just going to call this test. I'll have a bit of self weight, and then maybe also a couple random lateral loads as well. So I'll do, just to make this nice and easy on myself, 10 kilonewtons at a couple points in plane on this wall, and at a couple points out of plane on this wall. Now if I run the analysis, go to analyze, I gotta save the file, so let me just go give it a name. And here I've got my load case analyzed, and I can look at the deflected shape. Probably no surprises there. We can see how much is deflecting. It's less than the number of this units that I'm displaying here, but I can get the reactions and so on as well. And naturally, like I mentioned, we can look at shell contours. So here I can see, the instantaneous normal force on the x-axis of my shells. I can look at things like deflection. So I might want to look at x deflection or y deflection, for example, and see what's going on. And of course, I can see things like stresses if that's important to me. But what I think is helpful is being able to look at wall forces. And so with these wall forces here, I click on the wall forces tool and I can look at, for example, the wall forces in the local x-axis. And this will show me my in-plane shear force. So I only have in-plane shear force in this particular wall. And I'm looking at either just below or just above that wall location. So maybe just above the wall line location might be more relevant for the base of my wall. I can see things like moments. So I can see I have 100 kilonewton meters of moment at the base of this wall. I can look at axial loads and see how much axial load I'm getting for each one of these. And what might also be interesting is I could take this wall integration line result, I could right click on it, and I can go to concrete design and send those forces over to S-concrete for design. So this is really handy if we want to be able to design a wall, for example. These wall integration lines are really handy. Let's just say, for example, that we're looking at a slab, and I'll just use this slab as kind of my arbitrary starting point. Make sure I've got some cross sections defined. Yeah, I do. And also make sure I have some supports. Those are there as well. So if I go here to the load case, and for my slab, I'm going to say just look at self weight, click OK. And now I can go to analyze, and run a linear static analysis for just self-weight. Just wanted to do something really quickly here. Excuse me. And naturally, we can look at the same sort of results we saw for the contour. So I can see things like my Z deflections and different force and moment results that might be of interest to me. So I can see here how much moment I'm getting in different parts of my slab, as well as what I'll call wood armor moments, which can be helpful for designing slabs when you look at the inclusion of moments and torsion. And this will look at both the top and bottom of our slabs in different directions. But what can be handy here is we can cut a line essentially across one of these points and say, okay, you know what, I want to actually just left click on my contours. And here I can see kind of where those spikes are in my slab, not surprisingly around those column locations. And will just give me a better idea of how to design these perhaps in a more practical way, looking at points of interest rather than just kind of a topographical map. And these can also be implemented permanently in our model. So here I could go to the member definition tool, and I could set the member type at the top of the screen here to a strip integration line. And I may want to draw in a strip integration line. Let me switch to the top view here. That might be going, let's say, just through the middle of my slab, just as an example, because it's quite easy for me to demonstrate, and maybe another one over here as well. And I'll reanalyze this, this model. And now rather than having to left click on my mesh to produce those types of diagrams, I can actually go to the strip beam integration line forces tool. And here I might want to actually dial up the number of elements. And we can see those concentrations around the beams and so on. In this case here, we're looking at the top wood armor, which is basically the moment demands at the top of our slab in the x-axis. It's a handy way to kind of get that data out of S-frame once we've generated a model and so on. So there's quite a few kind of scenarios that we went through today. I do want to open up the floor for more questions. We have two that haven't been answered yet that came in today. So thank you, first of all, for all the people that submitted their questions in advance. And the other ones, again, that submitted them during the session, we'll do our best to answer those.